Hi, welcome back. In this video, we're going to define coordinates relative to a basis, and we'll define a coordinate vector relative to a basis, and we'll find a transition matrix from one basis to another. So before we write down our definitions, let's just establish a few things. Suppose V is a vector space. B is some ordered basis for V, so B has n vectors in it, so V is an n-dimensional vector space. And we say ordered basis because we want to make sure we write the vectors in the same order all the time. We know which order we're using. And suppose U is any vector in the vector space V. The definitions of coordinates and coordinate vectors relative to a basis. So the coordinates for the vector U relative to the basis B are the unique scalars or coefficients C1, C2 up to Cn, such that U is equal to this linear combination of the basis vectors, C1 times V1 plus C2 times V2 plus ... up to Cn times Vn. So we know that those scalars are unique. There's only one way to write a vector as a linear combination of basis vectors. So that's what the coordinates of a vector are relative to a basis. So a coordinate vector, the coordinate vector for U relative to the basis V is the vector, we write it like this, is a vector in Rn. It looks like this. Each component is the corresponding coefficient from that unique linear combination. So note that the vector space I'm talking about can be any vector space. So V could be a vector space of polynomials, it could be a vector space of matrices, it could be any vector space, and U is any vector in V. But the coordinate vector relative to a basis, the coordinate vector for U relative to a basis, is a vector in Rn. All right, let's look at an example. So let's consider the standard basis for P2. Remember, the standard basis for P2 is the basis B consisting of the polynomials 1, x, and x squared. And so this is an ordered basis. We always write it in ascending degree order. Now let's look at the coordinate vector for the polynomial 3x squared minus 5 relative to that standard basis B. Since we know exactly how to write a linear combination for 3x squared minus 5 as a linear combination of those three standard basis vectors, we know it's negative 5 times 1 plus 0 times x plus positive 3 times x squared. We can just write down the coordinate vector. It's negative 5, 0, positive 3. The coefficients in the unique linear combination of those standard basis vectors. Notice that here the polynomial 3x squared minus 5 is a polynomial in P2, but its coordinate vector relative to the standard basis is a vector in R3. What about if we consider this basis for P2? B prime consists of the polynomials 1 plus x, 1 minus x squared, and x squared. This is a basis. These are three linearly independent vectors in P2 that span P2. Let's try to find the coordinate vector for 3x squared minus 5 relative to this basis. So I'm going to write the linear combination C1 times the first polynomial plus C2 times the second plus C3 times the third. And all I have to do is solve for C1, C2, and C3. So I can see that C1 plus C2 has to be equal to negative 5, my constant term. My x term on the left side is 0, so I see that C1 has to be 0. And for my x squared term, I have a negative c2 plus c3 has to be 3. So I'll write c3 minus c2 is equal to 3. And if I solve this linear system, I get c1 is 0, c2 is negative 5, and c3 is negative 2. So my coordinate vector for 3x squared minus 5 relative to this other basis b prime is just the vector 0, negative 5, negative 2. Once again, it's another vector in R3, but it's a different vector. The coordinates are different because the basis is different. Well, let's talk about coordinate vectors in R3. So if we let B be the standard basis for R3, E1, E2, E3, remember E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. That's the standard basis for R3. And I want to find the coordinate vector for 3, negative 1, 5 relative to the standard basis in R3. Well, that's pretty easy because it's the standard basis. My linear combination is 3 times E1 plus negative 1 times E2 plus 5 times E3. So those coefficients are 3, negative 1, 5. So the coordinate vector relative to the standard basis is just the same vector, 3, negative 1, 5. But what about if I use a non-standard basis? Let's say B prime is the basis 1, 1, 0, 0, 1, 1, 0, 1, 0. So this is another ordered basis for R3. And I want to find the coordinate vector for 3, negative 1, 5 relative to B prime. So 3, negative 1, 5, the coordinate vector for that relative to B prime, I'm going to set up my linear combination, C1 times the first basis vector plus C2 times the second basis vector plus C3 times the third one has to be equal to 3, negative 1, 5. And so I set up the linear system and I get C1 equals 3, C1 plus C2 plus C3 equals negative 1, and C2 is positive 5. And I can write the augmented matrix for this system. So notice that the coefficient matrix, the columns are 1, 1, 0, 0, 1, 1, and 0, 1, 0. So those columns are the basis vectors in the basis B prime. So there's V1, V2, and V3. All right, so if we solve that linear system, we get C1 is 3, C2 is 5, and we solve for C3 using that equation, and we get C3 is just negative 9. So now my coordinate vector for 3, negative 1, 5 relative to this new basis B prime is just going to be the vector 3, 5, negative 9. So notice that coefficient matrix with the columns, which are just the basis vectors, if we call that P, notice that that linear system just says P times 3, 5, negative 9, the coordinate vector, is equal to 3, negative 1, 5, the vector we started with. So if we multiply the coordinate vector that we got, 3, 5, negative 9, by that matrix P, we'll get back to the matrix we started with. The matrix we started with was 3, negative 1, 5. So that equation gives us a transition matrix. So P, it turns out, is called a transition matrix, and it takes us from the basis B prime to the basis B. So if we have a coordinate vector relative to the basis B prime, and we want to write it relative to the basis B, we line up the columns of the basis B, as the matrix P. But then when we multiply our coordinate vector relative to B prime by that matrix, we get the coordinate vector relative to B. So it looks like this. That transition matrix times the coordinate vector relative to B prime of U will get us back to U, where U is the coordinate vector relative to B. All right, but what if we want to go from B to B prime? Well, notice that P is an invertible matrix because the columns of P are form a basis for R3. So the columns of P are linearly independent, and we have a major theorem that says that means that matrix is invertible. So if we want to go from B to B prime, we just need the inverse of that matrix, P. P inverse is the transition matrix from B to B prime, because if we start with this equation, P times the coordinate vector relative to B prime is equal to the original vector, multiply both sides by P inverse, and we get the following equation. We get P inverse times the vector U is going to give us the coordinate vector of U relative to B prime. So how do we get the inverse of P? Well, we actually have a theorem. Theorem 4.21 tells us how to do it. We perform Gauss-Jordan elimination on the big matrix we get by lining up the columns of B prime and then the columns of B. So on the left are the columns of B prime, on the right are the columns of the basis B. And we do Gauss-Jordan elimination until we get the identity matrix on the left, and that means we'll have P inverse on the right. Let's do it on an example. So in this example, we're on R3 again. It says find the transition matrix from B to B prime for the following bases. So B is the standard basis for R3, and B prime is a non-standard basis for R3. So we want a transition matrix to go from B to B prime. So according to the theorem, we line up B prime, the vectors in B prime as the columns on the left, and the vectors in B, the standard basis, as the columns on the right. So it looks like this. And then we do Gauss-Jordan elimination, and on the left we'll have the 3x3 identity matrix, and on the right we'll end up with P inverse. So the transition matrix to go from the standard basis for R3 to this other basis, B prime, is going to be the matrix P inverse. All right, so we'll be using transition matrices in Chapter 6. So this is an important concept, and we'll revisit it. I'll see you in another video.